So let's talk about the modulus of elasticity, and this is commonly known as the Young's modulus. I tend to use the term elastic modulus, but these are terms that are used interchangeably. So when we have a look back at what's called Hooke's law, Hooke's law is basically saying that as long as a material does not exceed what he's defined as the constant of proportionality, the applied force on a given material, which is causing the material to deform, will be directly proportional to the measure to which the material is extended. Okay. In that context, okay, if we assume that for that given component there's no change in the sectional area profile, then the stress will also be directly proportional to the measure of strain that the material is being subjected to, or the amount of strain that the material is experiencing. Thus, sigma, which is the stress, is proportional to epsilon, which is the strain. Thus, when you plot the characteristic curve, the expectation for materials is that the material, more other than elastomers, would exhibit a linear curve or a linear profile. The gradient of that curve is what characterizes the material's resiliency, thus the elastic modulus. Okay, so the elastic modulus, as I define here, is the measure of the material's resilience against deformation. So as I've more or less stated out, these are terms that are used interchangeably. So the Young's modulus characterizes the elastic modulus or the modulus of elasticity. In terms of engineering science or physics, the elastic modulus of the Young's modulus is characterized by the letter capital E. And capital E is simply the ratio of the applied stress to the resultant strain. Okay. So mathematically, the Young's modulus is equal to the stress divided by strain. And in terms of the units for the elastic modulus is denoted by gigapascal, because it's a very large number. And giga characterizes a billion. So mega is million, giga is a billion. Okay. So as I've more or less inferred, this can be related to Hooke's law to a certain extent. But in this diagram, it's showing a typical characteristic curve for some form of ferrous alloy. So what tends to happen is, if the material is behaving elastically, then you're going to have a linear profile, and the profile will continue to be linear until you get to what's called the yield limit. So the yield point is basically the material's transition from elastic failure or elastic deformation to plastic deformation. So when the material starts to experience plastic deformation, it permanently sets. There's no, the material loses its capability of recovering back to its original state of being. So let's assume that the material does not exceed its yield point. Then that means that once we take off the deforming load, the material should be capable of returning back to its original state. So if we work out the gradient of that linear profile in terms of the material's profile defining its elastic behavior, that gradient defines the material's resiliency. So as I've more or less pointed out, The stress will be proportional, directly proportional to the strength in the tube as well, when the force is proportional to the extension that the material is experiencing. We know from basic mathematics that the equation of a line, so y is equal to mx plus c. So where there's no load in this constant, the material is assumed not to be pre-stressed, so there won't be any c constant, if you want to call it that. So if we replace y and x, so on the y-axis is being characterized by stress, x-axis is characterized by the strain. If we work out the gradient, then the gradient defines the material's resiliency, thus the Young's modulus. So hopefully that is clear. So from our previous example, let's see if we can work out what the elastic modulus is, or the Young's.
Now let's look at working out the elastic modulus of the material. So we know two things. We've calculated the stress of the bar, and the stress is calculated to be 31.83 MPa. So we know that. We also calculated the strain of the bar to be 2.3334 times 10 to the minus 4, approximately. So how to calculate the elastic modulus? So the elastic modulus is characterized by E, so don't forget that the elastic modulus is the same as the Young's modulus. That's equal to the stress divided by the strain. So let's call that 1. So all that we have to do here is substitute our known values into this equation. This is equal to 31.83 times, so don't forget mega, is 10 to the power of 6, all divided by 2.3334 times 10 to the power minus 4. What we have to do now is box in our numbers. So this is 31.83 times 10 to the power 6 divided by 2.3334 exponent minus 4. And this gives us 1.3641 times 10 to the power 11 PA. And can rewrite this as 156.41 times 10 to the power of 9 PA. So 10 to the power of 9 is giga, so we can redefine that as 136.41 GPA. And there we have it. So if we want to know what the material is, we can use any reputable material database to find materials that have a Young's modulus, elastic modulus, equivalent to 136.4 GPa. And there you have it.
The Young's modulus. Knowing what the strain is, so we calculated the strain to be 31.83 MPa, and we calculated the strain to be 2.33 yada 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 to the power of minus 4. So let's work that out. Okay, so summarizing, Young's modulus is equal to sigma divided by epsilon. So that will be 31.83 times 10 to the power 6 divided by 2.334 times 10 to the power minus 4. And if we do the needed computation, we get a value of 336.4 GPa. So we can use this information relating to any reliable material database to find out what type of material has a Young's modulus close to this value. Okay, so that could be a task that you guys can undertake. So let's talk about strain energy. So strain energy is quite straightforward. It's just basically the amount of work needed to cause a material to deform. So that's essentially what the strain energy is about. So I've defined the strain energy as the capability or the capacity of work required in deforming the material. So if we were to assume how much energy is needed to flatten materials, and we're looking at designing and fabricating something with utensil, if we know how much energy is required in causing the material to deform to give us that bold profile, then we can use this concept in making that possible. But relating this to material failure is the amount of energy that the material absorbs to cause it to strain in some manner or form. So there are a variety of formulas that we can actually use in working out the strain energy. So we've got the first equation here, where the strain energy, denoted by U, is equal to half times F times delta L. And this formula is more or less relating to area under the force extension curve as defined by Hooke. So when we looked at the stress strain curve, we realized that once the graph getting to the yield point is linear, if we close that loop, it gives us a triangle. We know that a triangle, in working out the area, is equal to half times the base times the height. So the height is characterized by the measure of force, and the base is characterized by the measure of extension. Hence this formula. Alternatively, we can use this formula too, so they're more or less the same thing. So in this formula here, we're looking at if we know what the stress is, if we know what the material's resiliency is, and if we have some information to work out its volume. So this formula denotes stress being equal to sigma squared, or the stress squared, times the volume divided by 2 times the elastic modulus. Either equation based on the information provided will give you more or less the same result. And since we're dealing with energy, the unit for strain energy will be in joules. So let's see how we can work out the strain energy for the example that we worked out previously. So what do we know? We know how much the material is extended by. So the material is extended by 0.35 millimeters. We know what the applied force is. So in terms of generating that change in length to give us that change of 0.35 millimeters, that requires a force of 10,000 newtons or 10 kilonewtons. So we know that. So that information can enable us use U is equal to half F times delta L. Alternatively, we've calculated the strain. We've calculated established the elastic modulus, and we also know the measure of stress that the material is being subjected to due to the 10 kilonewton force. So we've got all the needed information to use either equation in establishing the strain energy.
Right, folks, so we calculated the stress of the bar to be 31.83 MPa. Okay. So, for those of you who don't know, this is also the same as 31.83 mega newton per meter. Right, so it's more or less the same thing. We also calculate the strain due to the applied force to be 2.3334 approximately times 10 to the power minus 4. And we also calculated the Young's modulus, or the elastic modulus, which is characterized by E, and that was 136.41 GPa. We're now being tasked to calculate the strain energy. So how much work has the bar experienced due to the 10 kilonewton tensile force that's caused it to elongate? So we're going to look at this, or calculate the strain energy, using two methods. The first one based on the concept of Hooke's law, and one based on knowing the stress, the strain, or the elastic modulus. Okay, so let's work that out. So the strain energy and that is USD, so that's how I tend to define strain energy. That's equal to half times the applied force times the change in length. Okay, so F delta L over 2. So let's call that equation 1. We know what our force is, so we know that force is our 10 kilonewton tensile load, and we're also given the the change in length, which was 0.35 millimeters. So all that we have to do now is substitute known values into our equation. So therefore, the strain energy is equal to 10 times 10 to the power 3 times 0.35 all divided by 2. So box our numbers into our calculator. So times 0.35 times 0.5. Okay. And that gives 1,750 Newton millimeter. Okay, but we need to change that so that we can convert the unit into joules. Okay, and joules is the same as Newton meter. But to change that from millimeters to meters, we have to divide that by 1,000. Thus, from Newton millimeters to Newton meter, which would be our joule, 1,750 Newton millimeter equal to 1.75 Newton millimeter to 1.75 J. Okay, so here we go. So we've used one method in calculating the strain energy. So let's see if we get the same answer if we use an alternative formula. So strain energy, knowing the stress and knowing the Young's modulus, we can calculate the strain energy. So the strain energy, U Sanskrit SE, is also equal to the stress squared times the volume of the bar divided by 2E. So how do we go about calculating the volume? Well, first let's list down what we do now. We calculated the stress, and that was 31.83 MPa. We calculated the Young's modulus, or the elastic modulus, and that was 136.41 GPa. So all that we need for this particular equation, so let's call this equation 2, is the volume. So the volume of the bar, V, be equal to the cross-sectional area times its distributed length. Okay. We know that A, we calculated A, and we got 314.16 millimeters squared. And we know what the original length is. So the original length is equal to 1.5 times 10 to the power 3 millimeters. So all that we have to do is to calculate the volume, or if we want to, we can just substitute all values into our equation. But let's work out the volume. So therefore, the volume is equal to 314.16 times 1.5 times 10 to the power of 3. And all that will be in millimeters cubed. So let's get our calculator. Let's box in the numbers. So we have 314.16 times 1.5 times 10 to the power of 3. And that gives us 471,240 millimeters cubed. But what I want to do is I want to work in the basis of meters, so I have to divide this value by 1,000 to the power of 3. So this becomes 471,240 divided by 1,000 to the power of 3. Okay? Or we multiply that value by 10 to the power of minus 9. And this becomes So divide by 1000 to the power of 3, and this becomes 4.7124 times 10 to the power minus 4 meter cubed. Okay, so we know what our volume is, we know what our stress is, so we've got all the values that we need to calculate the strain energy. So therefore, the strain energy from equation 2 will be equal to 31.83 times 10 to the power of 6, because that's a mega squared, times the volume, 4.7124 times 10 to the power minus 4, or divided by 2 times E, which we calculate to be 136.41 times 10 to the power of 9. Okay. So all that we have to do is do our computation. So the volume times into bracket 31.83 to the power of 6 squared. And that would give 4.7744 times 10 to the power 11, or divided by 136.41, yes, that's the 10 to the power of 9 times 2, and this gives 2.7282 times 10 to the power 11, so we can cast out that. Inverse times 4.7744 times 10 to the power exponent 11, and that gives 1.75 joules. So either method will give you the same result. Okay?
So in the first equation, we're going to work out the strain energy based on the applied force and the measure of the change in length. So if F is equal to, U is equal to half times F times delta L, U is equal to half times 10 times 10 to the power 3 times 0.35 times 10 to the power minus 3. And when we do the computation, we get 1.75 joules. So it takes 1.75 joules to give an extension of 0.35 millimeters. And remember what I said initially. It's very important to ensure that you convert your units when calculating energy into meters. If your information has been given in millimeters or centimeters or what have you, you need to make it your responsibility in converting the units from millimeters into meters. Alternatively, we can use what we know in terms of the strain, in terms of the stress, the Young's modulus, and the information to work out the volume. So we know what the length of the component is. The length is 1.5 meters. We know what the area is, so we can calculate and multiply the two to give us the volume. And we just put in known information into the calculator. And if you work it out, you get the same result, 1.75 joules. So depending on what information you've been given, you can use either equation to work out the amount of energy required is draining the material to yield the change of 0.35 millimeters. So hopefully that is clear. So this is a self-directed challenge. So I'll have a go with this activity to enable you recap some of the things that we've talked about. So in this particular example, we've got a specimen that's been subjected to some form of tensile pull, tensile force of 2 kilonewtons. The original length of the material or the component is given as 100 millimeters, and it has a diametric span of 15 millimeters. Okay, so the units provided are in millimeters. So the first task is to calculate the stress and the measure of strain of the material when subjected to the 2 kilonewton force. If the material was to be manufactured from Mars steel, and Mars steel typically has an elastic modulus which ranges from 195 to about 215 or 220 GPa. Okay? So once you've done that, see if you can calculate the change in length. And once you've calculated the change in length, have a go calculating what the strain energy is, which will cause the material to elongate. Right? So you need to see which of the formulas you can use in deducing what the strain energy is for the given specimen when subjected to a tensile force of 2 kilonewtons. So these are some answers. So these are the answers that you are likely to obtain. So in our next teaching event, we'll go through step by step in calculating the given problem. But for now, challenge yourself. All right, folks, so this is a very quick summary in terms of what we've discussed. So we've had a look at typical modal failures that engineering materials and or mechanical systems tend to experience. And we talked about brittle fracture or failure. We talked about ductile failure. We talked about fatigue. So materials do get tired over time, depending on how long they need to be subject to some form of force over a period of time. And we've also talked about creep. Okay. We've also looked at what stress means. So what is the correlation or the distinction between stress and strain? And we've also had a brief look into what constitutes the Young's modulus. And as I stated, I tend to use the term elastic modulus a lot. So once you've done all of that, you have a good understanding in terms of the basic fundamentals relating to reducing the stress and the strain mathematically. Have a go through the self-directed challenge. And as I stated, I will put another video showing you step by step how you go about working through the self-directed challenge. So in our next session, we'll talk a bit more about stress analysis in terms of one-dimensional stress or uniaxial stress. Okay. So on that note, stay blessed and catch you next time. Bye.